Hello! On my old YouTube channel, I used to do some videos which were moderately popular on engineering related things, including robotics and um, electronics and things like that, things of that nature. And I want to one up that now and move everyone over to this channel because I'm going to be making videos that are slightly more professionally done and more thorough. So for continuity, I'm going to start from the basics and we're going to do a practical transistor tutorial today featuring Arduino. Now this is an awesome electronic simulator that you can use in your browser called Falstad, and I'm a little surprised that it's working in Chrome here uh, before it was written in Java, and it looks like they've updated it to HTML5, which is pretty awesome. So let's take a look at what a transistor is. Right, there are different types of transistors, and they're considered active electronics. So the six types of transistors that they have here, which really boil down to three, are bipolar transistor or BJTs. You have MOSFETs and you have JFETs. For this video, we're just going to take a look at NPN bipolar transistors, and I'll talk a little bit about some of the others that you can get as well. Right? So this is what a transistor circuit diagram looks like. It has three connectors: the base, the collector, and the emitter. Okay. I'm going to explain what those are, but first let's take a look at another example. Okay, so this is our power source, and you can see that we have a live wire here. This is green, indicates a high voltage, and as we know with batteries, the longer wire in the power source indicates positive. So when I close the circuit here, let me just slow down the current speed because it's a little hard to see. What these yellow dots indicate are not electrons. This is the flow of positive current, which is more of a conceptual thing. Really, it's arbitrary whether electrons are flowing clockwise or counterclockwise in this circle. But here's the idea, right? When I close the switch, positive current flows through the battery, through the lamp, and out the switch here. Now take a look at this version of the same circuit. I've removed the switch and I've replaced it with a transistor. And of course the transistor has a third wire, the base, which needs to be plugged into something. So I've plugged it into the positive power supply here. So this is the this line right here is the positive line through a switch. And you can see what the transistor does here when I close this. It actually acts as a switch. All right. So essentially when positive electricity flows into the base and out through the emitter, it allows current to flow from the collector through to the emitter, just like the switch did, sort of, except this actually takes a little bit of current and allows a small current to control a larger current. So I'll show you how that's useful in a couple other examples. Obviously, right now we're still controlling it with a switch ultimately, but there are quite a few more applications. Namely, if this wasn't a switch, you could actually control the transistor with more complex logic, more transistors, and do some really interesting things. And that's how modern computing works. Before we move on to some examples, we need to look at some theory. So take a look here on the right. Here are a couple pictures of transistors. We have um, a cool looking dip style of transistor here with three pins, and this can be soldered onto a circuit board, and it's designed precisely for that. Not all transistors look like this. You can get tiny little transistors, and you can even build transistors into a silicone wafer, which you can have billions of transistors on one wafer. Um, Above that, we have the circuit diagram for a transistor with the collector, base, and emitter all labeled here. So let's take a look at some of the rules of transistors. First of all, there are these black boxes with three pins. Sometimes the pins are not labeled, so if you ever buy a pack of these transistors, which you can buy hundreds of them on eBay for pretty cheap, um, you might not have the C, B, and E's labels. So you should always check the manual, also known as the data sheet, for the transistor, what you can get is you type in the model number of the transistor, you'll get the manual, and it will tell you which pin is which and how to read it, and then you can use that to set up all of your circuits. So another rule is that any current that flows through base flows out of the emitter. All right, and similarly, maybe it goes without saying, any current that flows through the collector flows out of the emitter. Now, I mentioned that there's different types of transistors, and this is only one type. This is the a bipolar junction transistor, BJT, and it's an NPN, meaning that current flows into the base. There's another type of BJT transistor called a PNP, where current actually flows out of the base, and maybe I can touch on that a little bit later. But there's different types of transistors, but in this example, this is referring to NPN. Current flows through the base and into the emitter. What that does is it allows current to flow from C to E. And maybe at a later date, I can do another video talking about the mechanics of how that works inside of the transistor. But you can think of it kind of like a switch that when current flows through B, it basically it creates a region that allows electrons to flow through a piece of silicon inside inside the transistor's casing. Okay. The amount of current that flows from C to E through the switch is typically no more than 100 times the current that goes into the base and out the emitter. This varies from transistor to transistor, but typically it's around 100 times. So if you had a really, really, really slow current going into the base, then in theory, you could kind of use the transistor sort of as an amplifier, and there are different applications to that as well. And the final point I just want to make here is that transistors actually produce a little bit of heat when you're using them. And each transistor has a rating for how much heat it can take. In fact, how much current it can take, which you can use in your calculations. And if you exceed that limit, the transistor will heat up and it will actually burn out. And it's quite easy to burn these out, and they get quite hot, and you can burn yourself on these. And so in the past, I've had transistor marks in my fingers from overheating transistors. Even something as little as 6 volts can be enough to heat up one of these transistors hot enough to burn you. So you got to be careful when you're working with them. Don't make any mistakes when you're wiring them, because they will burn out your circuit. And they're pretty easy to burn out, so be really careful. And again, if you buy the really cheap transistors for a project that you're working on, you got to be wary of that. Alright, now we're back in Falstad, and we're going to do a bit of playing around with some components here. First, on the left-hand side, we have a sequencer, and I'm using this to simulate a signal from a microcontroller. Microcontrollers typically output about 5 volts, and if you look in the bottom right there, this is either outputting 0 or 5 volts, and it follows a certain pattern based on a clock signal. So this is like a representation of a microcontroller. All right, here's our motor. It's a resistor is a pretty good approximation for a motor when you're driving the motor at top speed. It's not a perfect representation because the resistance within a motor changes based on the load that the motor is lifting. So if you're lifting a very heavy load, in other words, if the motor is being stalled, the resistance actually goes down, and it will start consuming more power. And here we got a battery, and I just made a 12-volt battery. So we're going to say that, let's say we chose this motor for our project, and this is a 12-volt motor, which has a 10 ohm resistance to it. Okay. First thing you might do if you were trying to set up a circuit and you hadn't done anything like this before is try to drive your motor directly from your microcontroller. And as you can see, this seems to work. But this is a really, really bad idea. Okay, if you look in the bottom right, you can see that the amount of current going through this wire here is 500 milliamps. And I mentioned before that transistors will heat up if too much current is going through them. And the microcontroller is really built out of transistors and diodes and solid state electronics. And 500 milliamps is too much for those transistors in that circuit to drive. So this is a very fast way to burn out a microcontroller by driving half an amp through it. So you should never do that. Never do that. That's a very fast way to burn out a microcontroller. No, in order to drive a motor, you need to use a driving transistor. So let's add a transistor to the equation. So we got our NPN BJT transistor here. The way I'm going to arrange this is so that, oops, we're going to have a high volt line here coming out of our battery, our 12 volt battery. Let's move this here. Oops. Starting to lag up a little bit, understandably. Oops. Let me just pause the simulation. Okay, how about this? Does this look like a good circuit to you? Think about it for a second. Okay. It will drive the motor, but here's the problem. Transistors don't have a lot of internal resistance. So what happens is you have your microcontroller driving the BE current, and there's no resistor in this equation. So if you look down in the bottom right, you can see that the current going through here is infinite. And this is actually a short circuit. It's a very fast way to burn out not just the transistor, but the microcontroller. There are a lot of ways to burn out a microcontroller, and this is one of them. So what we need is a resistor here. So that's an easy problem to fix. Just add a resistor, no problem. Okay, and actually I'm gonna just reorganize this to make it nice and easier to manage. All right, how's that? Nice circuit, right? It works. Well, it turns out that this is not the best design for this circuit, and here's why. Well, first of all, I just chose an arbitrary resistor size without even doing any calculations. How do you choose the size of this resistor? But I mentioned that the current going through CE in the transistor, which is going to be the current going through the motor, which defines the amount of power getting transferred to the motor, that's going to be equal to 100 times the current going through BE. We haven't done any calculations to find out what that needs to be. So let's take a look into that. First of all, we know that we have a 12 volt battery and 10 ohms. So we all know the equation that V is equal to IR, current times resistance. Okay. And in this case, we're actually looking for R. So IR equals V over R. Sorry, I equals V over R, which is equal to 12 over 0. Oops, no, not. So 12 volts over 10 ohms. I don't know why I said 0. And that's going to be equal to 120 milliamps, right? So 1.2. Oh, sorry, my mistake. It's actually 1.2 amps. Now, in order to drive 1.2 milliamps, the amount of current coming into the transistor needs to be 100 times less than that, at least 100 times less than that. So let's do another little quick equation here. We'll do, so we have I equals, well, we know 100 times less than 1.2 amps is 12 milliamps, right? So when we're calculating the resistance of the base transistor, sorry, the base resistor here, we would get R equals V over I, over I which is equal to 5 over 0.012, and that's going to give us a resistance equal to around 417 ohms. So just pause the video, make sure you understand that, and I'm just going to change this. So 417. All right. Now just for testing purposes, I'm actually just going to set this to on at all times. Ooh, okay, good. So you can see in the bottom right, it's actually telling us what the current is here. We're getting 1 amp. Now, if I change this to, let's say I change it to a little bit more, 500. Now we're only getting 850 milliamps. But if I change it the other way to around 300, it should only be giving us a little bit closer to 1 amp. It's actually giving us the nominal, almost the nominal 1.2 amps. So the lower we go here, the more the current will be, but it will converge with 1.2 amps. So 417 is the minimal amount. Sorry, it's the maximum resistance theoretically, but again, transistors are not perfect mathematical units. They have a little bit of error and so on. So because they're made out of physical materials. So we want to go a little bit below 400, so around 200, 300, and we're going to get our 1.2 amps going through this wire. And it turns out that the current going through the base of the transistor, in this case with 300 ohm resistor, is 14 milliamps. And that's a lot more reasonable than trying to drive all 1.2 amps or something like that through the by the microcontroller. Now I want to take a moment to analyze the positioning of the components in the circuit. What would happen if we took this and put it down here? All right, would that work? Well, yeah, it drives the motor still, but notice that the current going through the motor is a lot less. We're not getting 1.2 amps anymore. We're only getting 330 milliamps. Can you think of a reason why that might be happening? Pause the video now and try to think about it for a second. Well, for one, we added an extra bit of resistance to the microcontroller. So now the microcontroller not only has to drive this 300 ohm resistor, but the current has to come down here and go through this 10 ohm resistor. And in fact, this is going to be a variable 10 ohm because it's a motor. So it's a little unpredictable there. But that doesn't really add up. If you do the math, you have 310 ohms and 5 volts, and the current should be a lot higher. And if I highlight over here, you can see that it's 3.2 milliamps going through this resistor. So something else kind of weird is going on here. And it turns out that all we've done is we've created kind of a weird resistor network where you got the 12 volts up here fighting with the 5 volts here over where the voltage drop should be over either the transistor or the resistor. And this has come to sort of an equilibrium of sorts. And if you look here, you can see the weird voltage drops over each terminal of the transistor, right? Like, okay, 8.7 volts being dropped over CE and only 3.3 volts being dropped over the load. So we can do an analysis on this, but I think it's enough to say that this is not the proper usage of this resistor, of this transistor, at least not for the applications that we're looking for. Now there's a really important thing that we need to consider when we're evaluating the circuit, and that is we know that the microcontroller needs to be driving at least 12 milliamps and probably a little bit more in order to get the motor spinning at full speed and power. But we always need to check the specification for the chip that we're using to make sure that it's capable of driving that much. 12 milliamps might not seem like a lot, but Microcontrollers really aren't designed to be driving a lot of current. They're devices that are meant for logic and digital communications and things of that sort. So when we're interacting with things like motors and other physical devices, we have to double check the specifications. And certainly there are chips out there that don't drive 12 milliamps and that would just burn out the entire chip. Now I happen to know that with Arduino, at least with most Arduino models, the the pins are able to drive as much as 40 milliamps before we burn out. So we have a bit of a safety factor there, but it's not really a risk that you should take. Check it, and we could do a bit of a thought experiment as well to find out what would happen if, say, that we had a chip that couldn't drive 12 milliamps or 15 milliamps. Let's say that it could only drive 10, and we wanted a safety factor on top of that. What would a circuit look like that would allow a microcontroller with such limited um, current producing ability to drive a 10 ohm 12 volt motor? Let's take a look. Now here we're going to add the limitation that the microcontroller should really only be driving about 10 milliamps. And you can see here that it's driving about 15 milliamps if you look in the bottom right. We can change the resistance of this resistor, but then you're going to get a very low current going through your motor. It's not going to be driven at full power. Turns out that there's a relatively simple trick that we can do to fix this, and I'll show you what that is. We need to use another transistor. I'm going to stop it just so I can set up the circuit. So here's our live wire, and I need to power this transistor, and I'm not going to use a wire for that because that would be a short circuit, right? So we need a resistor here. We can experiment with values for these two resistors in this new setup, but let's take a look at what happens when I run this. The current going through the motor is now exactly 1.2 amps. The current coming out of the microcontroller is 3.55 milliamps. So how does this work? Pause the video and try to see if you can analyze this circuit and try to understand what's going on here. Well, let's start from here. We have a 1000 ohm resistor with 3.55 milliamps. So we know that the current going through CE here can be 100 times more than that, a little bit less than that because it's not perfect. And if I highlight over this resistor, you can see that the current is a little bit over 100 milliamps, which is what we'd expect. Now this transistor is just being driven by that 100 milliamps. So that's enough to have this second transistor running at full blast. 100 times more than 100 milliamps is 10 amps. And so the maximum current that this transistor will allow is 10 amps. Most transistors can't take 10 amps, they'll blow up. But what that means is that this is operating in switching mode. So this is an on switch. Essentially, it's not. This one's working as an amplifier, and this one's working as a switch. And as a result, you have all the current, all the voltage being dropped over this load resistor, and it's getting the maximum current of 1.2 amps, which is what we needed to drive it at full blast. In fact, even if I change this resistance to 1000 ohms, right, the current going through here is still 11 milliamps, which again was around the rate amount to drive this transistor, and we can see that we're still getting 1.19 amps going through our load resistor. And this is what that sample would look like if we were to wire it up with an Arduino. This is running the default Blink sample code, which you can find under the Arduino file menu, under examples. I changed the battery to 9 volts because this is a more standard and readily available power supply that you might have. And I'm not really sure what the specifications of this motor are, but you get the example. Also, we don't need the second transistor here because remember, Arduino should be powerful enough to drive the necessary 10 or 15 milliamps that we need to drive the motor at full power. By the way, this is a really cool circuit simulator that I found while I was surfing the net. It's made by Autodesk, and you can use this in your web browser. I hope that this video was helpful to you. Subscribe to my channel and check back frequently for more electronics tutorials. Let me know if you have any questions in the comments and like my video. Thanks a lot. Bye.